So we resume with from Freiburg about the liquid tensor experiment again.
Yeah, so thanks again for the invitation. So today I close my talk reflections on the liquid tensor experiment. So I'm not going to repeat what I said yesterday, but well, I think we're getting pretty close to the end of the liquid tensor experiment. We can already start looking back a bit and see what kind of lessons. But a little warning. First of all, I take a very pragmatic approach to these things. So just like Patrick, I wouldn't be able to actually give you any axioms of Z of C, and the same is true for type theory. But we will talk a bit about type theory and set theory. And none of these reflections have been formally verified, so make of that what you want. First of all, I think, so type theory has been coming up a couple of times, and I just want to give a little crash course, and then after that, share some thoughts about how things we've learned over the period of time that we were working on the liquid tensor experiment. And yeah, this crash course is also needed for my first reflection. So that's one of the reasons I want to do it, but also because it has been coming up a couple of times today already. So maybe just good to clear up some confusions. So in set theory, everything is a set. That's basically the slogan that you need to know to be able to work with set theory. Or well, at least it's to be able to defend yourself when someone says, okay, how do you make this precise? You say, well, everything is a set, and then I think the stacks project starts with 3 pages where they explain why a scheme and a sheaf actually is a set. And a scheme is something like a 5-tuple consisting of a topological space and a sheaf, or I don't know. And then, no, okay, maybe it's only a pair, and then a sheaf was maybe I don't know. In type theory, everything is a term. So yeah, what's the difference? But no, there is one difference, and that is that every term has a type. And okay, so what does it? We'll see in a moment what that means. But let's first see why set theory has some issues, because we saw that we have like we can write down integrals in type theory that don't make any sense, that they're just defined to be 0. And other statements that are really garbage, but set theory actually also has these problems. I mean, should we be able to write down this formula in set theory? And if we do, is it true or not? And I guess this depends on whether you learned about natural numbers in England or in French or in France, because it depends on your definition of 2. And for one definition of 2, this is a provable formula. And for another, it isn't. So what about 2 as an element of pi? I guess everybody agrees that that one should at least be false. And the intersection of the square root and pi, is that a meaningful thing to consider? Or the fact that 3 is a topology on 2? It again depends on your definition of the natural numbers, but there is a definition of a very common definition of natural numbers where this statement, it doesn't only like, it is a syntactically correct statement, it's actually true. 3 is a topology on 2. So, should we be able to write these things down? And type theory says, no, this is just garbage, this is nonsense, you shouldn't be able to write this down. These formulas are not type correct. So, you have this innate sense that there was something garbage about these formulas, and that innate sense means that actually you're a type theorist. You just don't know yet. So the thing is that if you try to write down these statements in Lyon or another system that is based on type theory, you'll get a syntax error. It says, what you just wrote down doesn't make sense. So I'll try to give you a sort of intuitive, like a bit more of an expanded intuition about what type theory is. If you've done some programming in programming languages, like in C++ or something like that, then you're already familiar with the type system. Because you can define a function that calculates the length of a string. And so it only accepts as input values strings and the output value will always be an integer for the C++ definition of integer. Those are sort of data types, and as mathematicians, we really like other kinds of data types, but things like the integers, the real numbers, continuous maps from X to Y, or a vector space V, these are all sort of types that have elements for a suitable notion of elements. But then there's another sort of types in Lyon, and those are propositions. And propositions can also be viewed as types. And so we can write down X to the n plus Y to the n of Z to the n, or 2 plus 2 is 5. I mean, this statement is not true, but it does make sense to write it down. It's type correct. It's a false proposition, but it is a proposition in the sense of logic. Things like f is C linear or whatever, that all numbers greater than 3 are prime. And so the notation is you write down T colon little t colon capital T, and that means that little t has type capital T, or you say that T is a term of capital T. And so what are the terms of this type? Well, they're just integers. And these are just, the terms of this type are real numbers. So what are the terms of this type? Well, they're proofs of the fact that f is C linear. So you think of this as the set of all integers. You think of this as like the collection of an element of this set. If you view it as a set, would be a proof of this statement. And so in set theory, there's you have like two systems. You have set theory and you have propositional logic, and you need both of them to do mathematics. In type theory, these are sort of brought together, and so both your logic and your data kind of things are both in the same framework of type theory. So
when you say proof, it's a correct proof or it's an attempted proof?
So an honest term of this type would be a real, like a checked proof. Yeah, exactly. So at some point we'll talk a bit about expressions, and then anyway, so some simple examples. If X and Y are two types, then a very easy way of creating a new type is the so-called function type of, so this is a new type, and it's the type of all functions from X to Y. And one really nice coincidence with normal mathematics is that a term of that type, you write a column. So that's another proof that you're just a hidden type theorist and you didn't know that. You've been using the notation all the time. And so the terms are expressions like this. So where phi of X, I mean, phi is not, I now don't mean it as a function, it's just a piece of placeholder notation for some sort of expression, and that expression should be a term of type Y for all X. So for example, I mean, if X and Y are both the natural numbers, then this could be the expression X plus 2, and then that gives you an example of a function. And so computer scientists have their own notation for this. Instead of the very nice match to symbol, they choose to like use the lambda symbol so that you cannot use it for anything else anymore. But okay, I survived that, I guess. And the nice thing is, so if X and Y are not data types but prop types, then a function from X to Y, so now X and Y, maybe we should call them P and Q. So what is a function from P to Q? Well, it's a thing that takes a proof of P and returns a proof of Q. And so we recover implication between propositions. Because implication is just a function that returns proofs of one thing into proofs of another. Okay, so wait. Anyway, so two other examples that are really fundamental in type theory are sigma types and pi types. And basically all other types, okay, you need several other tools, but not too many. These are really fundamental tools to build new types. The way it works is you have some sort of indexing types. No, yeah, I'm not going to talk about inductive types, but of course you need inductive types anyway. these are two very important examples, and so you need an indexing type and then a function from that indexing type to the type of all types. So for every term little I of I, you get a type, and I'll just write x sub I for that type. So then you can build a new type, which is called a sigma type, and it basically means that you take the disjoint union of all these xi's. And so a term of this sigma type is a pair I comma x, where I is a term of the indexing type and x is a term of the type indexed by I. All right, so I mean, you just have x1, x2, 2, and x3. And if you want to give it a term of this type, it means, well, you first have to tell me in which circle I live, and then you have to give me something in that particular circle. And the other example is the product type, the pi type. And so the notation is that you now use a pi, and terms are now collections of little xi's for each term I in the capital I. And oh, sorry, I'm missing an index here. So and xi has to live in the type xi. And so this is this really feels like well, products of sets that you're used to. And so somehow I guess it also really feels like what you see with vector bundles or other types of bundles, where you have a base space, and in this example, the base space would be I, and then you would have I xi, and sort of the fiber over little I is this xi. And so these are examples of so-called dependent types, because well, you have terms whose type depends on the term of another living in another type. But they're extremely useful, but they also cause some problems sometimes. So that's what we'll talk about in a moment.
You are between second in the word?
Wait, I'm completely confusing myself.
Pi is the space of sections.
Pi is the space of sections of the sigma type. Sorry. Yeah, thanks. Sorry for the confusion. So, okay, right. This is, I mean, the bundle is the disjoint union of the fibers. But then, if you want to take a section of the bundle, then you have to give a function from I to this thing. But every thing below, every point below, has to be sent to something in the fiber above it. And so the sections S would be a term of fiber. Yeah. Okay. Okay, so now I want to talk very briefly about type checking. So now we have two expressions, little t and capital T. And somehow type checking is a very simple and precise algorithm that can infer the type of little t. There is one little catch. I mean, unless t is not type correct, unless you have one of these garbage statements that we saw on one of the first slides, then you just get a syntax error. But otherwise, it can this algorithm can look at the expression and say, okay, I have the expression 2 plus x, maybe, and I know that x is a real number. That's right, explicit. Yeah, and then you start at the left and you see, okay, this is an x. Okay, so this is a real number. Then we have a plus. I don't really know what plus is, but I look up in a database and I see that plus is a function that goes from a plus a to a. Okay, so in this case, my a has to be the real numbers, And so the second thing is an element 2, and so that should also be interpreted as a real number, and the result is going to be a real number. And so then this algorithm can infer that this expression is a real number. Okay, the actual story is slightly more complicated, but one of the ideas is that this is really simple, and you can implement it in a couple of hundred lines of code in any computer language. And that's really the part that you need to trust, because in this case, I'm sort of writing a data term of a data type. But you could also imagine that you write an expression that builds a proof term of one of these proposition types. And so it will then infer that type. And okay, again, the whole thing in the end is slightly more complicated because we also have this capital T. And it doesn't just take little t and then infer the type and check whether that is equal to t, but it works somehow from both ends. But in the end, the most important thing to remember is you cannot prove that t is a term of capital T. This can only be checked. That's somehow something that took a while for me to understand. But the idea is you pass these two things to the type checker, and that is a very simple thing that doesn't know anything about mathematics. It doesn't even really know what. So all it does, it looks at those expressions. It starts inferring the type of little t and sees if that matches up with capital T. And so you can hand that off to the computer, and the computer says yes or no. But you cannot, like, if it cannot say, oh, I'm not sure, and then you give it some more, and then you start proving it. And so one issue is, if we know that t is a term of type capital T, and capital T is equal to t prime, does that mean that t is also a term of t prime? And now we get into hairy issues, because what exactly do we mean by this equality? And so the point is that certainly if t and t prime are exactly the same expression, like as syntactically the same, then I mean certainly this is also going to be true. So what if I take t and in t prime I take one of the substrings occurring in t, some word, and I replace that word by its definition. So I unfold the definition. Then I get a new expression, but it should really have exactly the same content as capital T. And so then it will still be true. Okay, but now what if I just have two completely different expressions, but I can prove that they are the same? Well, this proof is something that you cannot pass on to the type checker, and the type checker can also not discover it by itself. And that means that in those cases, this will not type check. And there are very simple examples. So, for example, if our I is the natural numbers, then we could have a fiber over 2, and we can have a fiber over 3. And at some point, maybe you want to look at the fiber over m plus n. And then at another point, you want to look at the fiber over n plus m. And of course, these are the same because m plus n is equal to n plus m. But m plus n is equal to n plus m is something that you prove. So so now if you have a term of this type, then the type checker doesn't understand that it should also be a term of this type, and it just flat out refuses that. And at least this is the case in Lyon, and there might be some other systems where it works slightly differently. But do you sort of understand what the issue is? That
couldn't you have inference algorithm that can accept proofs?
So at least in Lyon, that's not possible at the moment. And I think it makes this type checker a lot more complicated, and so also more bug prone. So from my point of view, this is sort of a nasty issue in type theory, and I am completely unequipped to start thinking about solutions. I do sort of understand why. Yeah.
Sorry. How often do you have to run the type checker?
All the time.
I mean, what the program is doing all the time.
Yeah, it's like every step in a proof, the type checker, or like every proof you write down, the type checker checks whether the proof is correct. Every definition you write down, everything has to pass through the type checker.
Somehow, this type checker is something implicitly in the system, but you can check by hand whether T is a T prime. You can prove. I mean, you can ask.
I mean, just for easier for the person to program, like I don't check it explicitly, it's done by the software, but you can check whether it is.
There is something more fundamental. There are two levels. The theory you're working in and the meta theoretical level. It's like if you're working in a more traditional thing, where you've got the first order logic laid on top of thermal axioms, then you can proving stuff inside your theory or proving stuff about the first order logic. They happen in two different worlds. And those two worlds they don't communicate in both directions. So logic being used inside the theory. So this situation is a comparable issue. There is this level where type checking happens. It's not the level you are working in. It's kind of a meta level theory. So you cannot negotiate on this meta level. You can negotiate only inside the theory you're working.
I mean, I guess like you could take one step back and start negotiating about which meta theory you want to use. But once you've chosen a meta theory, you can no longer.
Yeah, and at some point you need to stop. I mean, you cannot just go more and more meta and negotiate forever.
Yeah.
I mean, it is completely independent of the computer implementation issue, or even independent of the kind of foundation you want to use. I mean, at some point you need to start somewhere with a non-negotiable bit, and then work inside the theory.
So this sort of was a crash course in type theory to make sense of my first reflection, and that is that there's definitional equality. So there's notion that T1 is equal to T2 just because like the kernel, the type checker, can just unfold a few definitions on both sides and then recognize, okay, these things are just identical, exactly the same, without the need of any proof. This is a notion that doesn't exist in ordinary maths. We just prove that things are equal, and that's all we know about. But it really matters in systems like Lyon that are based on type theory. And so I think it matters more than it should, certainly from the point of view of a mathematician. But on the other hand, I mean, it's really great in general. The fact that you can just use all sorts of facts about real numbers when you write down this expression, and you don't have to all the time remind Lyon about all sorts of things. Lyon can use the fact, Lyon can infer that things are real numbers, and then if you want to apply a lemma about, say I want to rewrite this into t plus x, 2 plus x, and I want to use that addition is commutative, which is something about abelian groups. So Lyon just looks at this expression, infers that it's a real number, looks up in some database that the real numbers from an abelian group, says, aha, so this addition is commutative, and okay, you can rewrite with commutativity of addition. And I never had to, as a human being, explicitly feed the lean the fact that, oh, yes, it's an abelian group because of some fact written somewhere else. I mean, of course, we had to prove that the real numbers were an abelian group, but we did it only once, and then you don't have to mention that anymore when you apply lemmas about abelian groups, because it just knows that this is a real number and hence can look up in some database all sorts of useful facts about real numbers. And this is a baby case example of something that we use all over the place. So this type, the fact that things have types is an extremely powerful mechanism. So like if I would have to choose between set theory and type theory, I still think I would choose for type theory. But on the other hand, it's really biting us. So to explain an example from homological algebra, like one thing that you look at in homological algebra are so-called complexes, and just the easy example is you have a whole collection of abelian groups, say. And so you have abelian groups x1, x2, x3, x4, and then you have maps between them. And then there is a condition that if you compose two maps, then the composition is 0. But that's not even the important part at the moment. So we have to give these maps a name. And traditionally, you would call this B1, B2, B3. Okay, so now we need to do a little bit of type inference ourselves. What is the type of DI? So we write down a column because that's the way it works. And it's going to be a map from xi to xi plus 1. Okay, and now I want to talk about this fact that, so I'm over here and I want to use the fact that the composition of these two maps is 0. So the map coming in and the map going out. So I'm over at xi and I want to say that, so I have this map that is going out of xi. I want to compose it with the map coming into it. So that's di minus 1, and that is 0. So, okay, this is not a 0, this is a composition. But now Lyon says this is garbage. You cannot write that. And the issue is that di minus 1 is actually a map from xi minus 1 to, we have to substitute I minus 1 for all the i's. So it goes to xi minus 1 plus 1. And it's a theorem that I minus 1 plus 1 is equal to I. So, I mean, this is equal to xi by proof, but not by definition. And so the type checker cannot see that and rejects this as garbage. Okay, so that's really painful. And so the solution that we decided to use is that everywhere we add like, so we now talk about the map dij, and it just is a map from xi to xj. And so over here we can write di I plus 1 and I minus 1 I, and now Lyon is happy. Of course, you now need to explain what this map is when j is not equal to I plus 1. So there is another option that you add, like also a piece of notation for the proof that j is equal to I plus 1, but that's annoying and you don't want to check this all the time. So what we say is that dij is, well, if j is equal to I plus 1, what you think it is, and else it's just a zero morphism. And the nice thing is that the composition of two of these maps is always going to be 0. In the garbage case, and in the case where it makes sense. And in this case, I think it's actually defensible that it's a 0, because what you do a lot of the times in homological algebra is that you look also at like this direct sum of all these things, and you say this has a map, well, to itself, and then you define it exactly like this on the components. You say, well, from xi it goes to xi plus 1, and all the other components it's 0. So
zero. Aren't these zeros different zeros?
yes.
They are different zeros.
Yes, all the zeros are different types. So 0 is just a piece of notation for the 0 element.
So the zero you get there is the zero at j.
It's the morphism. It's the zero function between xi and xj, and which always exists because they're abelian groups. Yeah. And Lyon knows the expected type because I told it when I wrote down the definition, this is going to be the type. So I can really write down if blah blah blah, then okay, you cannot write down this, of course, but then and then else 0. I don't need to say what kind of 0. It knows, okay, this is the type, so I should look for a 0 element in here. And at some point we say, we prove that this is an abelian group because maps between abelian groups form an abelian group. And so it knows there is a 0 element. And so it knows that it has to pick that one. Okay, so there are solutions. And in this case, the solution worked out quite well. But it was pretty frustrating that it didn't work the way we normally wanted. And I think the cost is not too high in this case, but I still would like a solution. And so maybe there's something called extensional type theories, where it's this idea of like maybe you can feed proofs or maybe certain kinds of proofs to the type checker. And yeah, maybe we need to look into that. So that's sort of homework for people who care about kernels and type checkers, etc. I would love to discuss this with them at some point. So then the next thing is somehow a bit more mathematical. So in the liquid tensor experiment and in homological algebra and certain more categorical parts of mathematics, commutative diagrams show up a lot. And I mean, there's this phrase, diagram chasing, that we use in mathematics, where you have a diagram of abelian groups and you pick an element somewhere and you chase it around the diagram and you just follow your nose around, and in the end you've proven some lemma about abelian groups and maps between abelian groups. And one thing that you really use is sort of this pictorial two-dimensional representation of the diagram. And it really guides your intuition. But the way a commutative diagram looks like in Lyon is just, well, you have objects A1, A2, A3, A4, A5, A6, etc. And then below that you have a list of 15 maps between these objects, and then below that you have a list of assumptions that they form commutative squares or triangles, etc. And so all the two-dimensional intuition is gone. Well, of course, I can just draw a picture on paper while working on the proof, but both for writing down the statements, I would just want a good input method, and also then in the tactic state that you saw in Patrick's talk, I don't want this huge list of objects and morphisms. I just want a nice, I mean, it's basically a web browser that you see there. So we should be able to just draw a really nice diagram and use that in the proof. So the current situation doesn't scale. I mean, we can do it for this project, but if we want to do more, then we need to think about a way of making commutative diagrams native objects that are well represented in Lyon. And I think that's a very interesting project. And it's right for automation because the proofs usually are, there's only one step you can take that makes sense and all the other steps don't make sense. So if we can make that notion of which step makes sense slightly precise, then I think we should only need to write down the statement and then we can leave finding the proof to the computer. So the next thing is reasoning up to isomorphism. And this is something that happens all over the place in the liquid tensor experiment, but also in algebraic geometry, in algebraic topology. And you have all sorts of objects that are defined by a certain universal property. So you prove that they exist, and then if there's another object that satisfies the same property, well, then there's unique isomorphism between these two objects, so you can identify them and treat them as equal. And that's a way of treating things as equal that goes far beyond proving that two types are equal. It's like they're just not the same. In set theory, they're also not the same, but you can just canonically identify them. And so you want to do this.
You mean just like R2 and R2?
Exactly, R2 and R2. Right, so I mean, it shows up, I think it shows up a lot in algebraic geometry and topology, but it shows up in linear algebra already. And so for Votsky, when he started thinking about how to formalize mathematics on a computer, he was very acutely aware of this problem because the mathematics that he had done was basically doing this on every line, on like 100 times on every page. So he said, okay, this is a very fundamental issue. This idea of taking two objects and canonically identifying them is something fundamental to mathematical practice. So we need very good support for that. And together with other people, he developed homotopy type theory. So I think that's very interesting. But it's also at the moment, it's not suitable for as a foundational theory for huge formalization projects like MathLib, where we have over 800,000 lines of code spanning from probability theory to homological algebra, linear algebra analysis, topology, everything. Because like, do we really want it everywhere? Or do we just want it for algebraic geometry and algebraic topology? People doing calculus probably don't want to be forced to deal with the extra burdens that homotopy type theory would place on you. And so a question that I really don't know the answer to, but like, could we have homotopy type theory tactics that sort of are these sort of proof generating computer programs that will take care of all the troubles without really going all the way to the foundation? So can we have some sort of meta-theoretical tools inspired by homotopy type theory? Or can we just solve all the foundational issues? It's not something I think I'm, like, at the moment, I just don't know enough to work on these issues myself. And it's also like, I think I would lose interest at some point because I'm just not a foundational guy. But I'm certainly hoping that other people who really like working on this will solve these issues. And no, you shouldn't look at Gabriel. Don't feel pressured. Okay, another thing is we have a blueprint. We have something we call a blueprint, which is a LaTeX document that has some extra LaTeX macros for cross-linking, cross-referencing to the Lean formalization. And this was developed by Patrick, the software behind it. But it's a bit funny that we call it a blueprint because it was really written at the same time as the formalization. So sometimes it could have been more helpful if it was actually a blueprint that already contained a lot of details while working on the project. But I think even in the current way, it has been really helpful, if only to give a very clear overview of where we are, because we could generate a dependency graph out of this, which, I mean, it sounds trivial, but it's a really helpful way of understanding what has been done, what needs to be done, the order of things in which we need to do things, etc. So I think this this blueprint is a very good idea, and we can, yeah, I mean, other projects have already been using it, so it's a reflection, and I don't even need to make a recommendation because I think there are now maybe 5 projects already using your software, and yeah, at least it's.
I can see 4.
Yeah, so it's. I think it's very helpful. And yeah, whether or not you write all the LaTeX before you start formalizing, in the end, doesn't even really matter.
I think if you rewrite everything, it's a bit of a failure for the formalization project, because if formalizing the stuff doesn't make you realize that there are gaps everywhere and that there are better ways of explaining it, then it's a sad conclusion.
So another thing is refactors. So this is partly a reflection of the Liquid project and partly on Mathlib itself. One thing that I've noticed is that so I've worked on like some software projects in high school and as a student, etc. And they were way smaller, like maybe 10, 20,000 lines of code at most. And with Mathlib, we're talking about almost 2 orders of magnitude larger. But already with these projects, if you've written a bunch of code that sort of did the job, then it was really scary to start refactoring it and changing things to make one thing work better, because the risk is always that 3 other things become worse. And I think people have been surprised by the amount of refactors that we're able to do in Mathlib and also in the Liquid project, and we just do them all the time. They still cost time and energy, but they're much less scary than in traditional software development, because you have interactive theorem provers like Lyon give you such strong guarantees that the end result is at least as good as what you started with, that yeah, there's no need to be scared of them. And yeah, so I mean, if you change 3 definitions and you think carefully about changing these definitions, and then your favorite theorems are still true after you finish the refactor, then you can be sure that, like Lyon checked that you didn't break something. So then maybe 2 more things, and then I'll wrap up. So another thing that I found extremely helpful during the Liquid project is top-down development. And this is something I was warned against a couple of times when I started formalizing. But I think actually I now understand these warnings, and I want to explain them a bit and qualify them. So if you know your end goal and you really know the mathematics quite well, then as we've seen, there are still issues like stupid implementation issues about how you define things. But if you start at the top and you work your way down, then your end goal where you're trying to go informs the way you set up the definitions. And since you already know where you're going, and you're working your way down, you can make the definitions so that they work exactly the way you want them to. There is, of course, a risk that if you like made your top level definitions and stated your top level theorem, and then you're working your way down, but you made a mistake all the way at the top, then you work your way down, you find there's something wrong here and everything, and you have to change something, and all this doesn't match up, and you have a huge refactor to fix things. So that's the risk. On the other hand, I sort of also applied this approach with these green Lyon resolutions that I mentioned very briefly yesterday. So this is something in homological algebra. I'm not really going to explain the maths, but it was a complicated tool that the proof that Schultz had written, it relied on this tool. And our first strategy was just to write down the fact that these properties existed and then assume that as a black box and work with that. And then we would have one sorry left in our final formalization and accept that as a fact of life. But when I wrote down these axiomatization of the objects that we needed, I started playing around with it a bit. And I discovered that there was an object that satisfied almost all the axioms except for one. And actually that axiom didn't, as it turned out, wasn't essential. And so we discovered a new object, well, or at least a new description of an object that later people already knew, but we also discovered new properties of this object. So we discovered some new maths using this top-down approach, and I think with a bottom-up approach where you just follow the trodden paths all the way to the top, this is much less likely to happen. On the other hand, if you don't know where you're heading, then you should just go for a bottom-up approach. And this is also what we did a lot of the times when we really didn't understand the proof. We just said, okay, we'll just formalize the next 3 lines, formalize the next lemma, and we battled along until we figured it out. So then, in the end, you still, the risk that you run then is that if people are doing that in 3 different places, then they build up some work and it doesn't really match in the end. So, right, you might end up with two objects that are not the same but canonically isomorphic, so you have to translate things through this glue. But yeah, well, then duct tape maths. Okay, so that's just a bunch of thoughts that I had that I think can be useful for future projects. Yeah, this is maybe, let's just stop here. Okay.
Other questions for Johan?
Just to make things clear, what you call top-down is to write precise definition and statements, final segments at the beginning, and then filling.
Exactly. And so, but you can do this on many different levels. So, for example, Schulze told us, okay, here's the challenge, final big theorem. Before you do anything else, there's this really technical theorem that is the main key ingredient in the proof. So he sort of gave us the first top-down direction of saying, okay, this is where you should look at first. Then what I did was I formalized all the definitions in the statement of that theorem and formalized that theorem. So then we knew what our goal was. And then there were parts. So then for example, I continued my top-down approach with this Commelin stuff. But there were other parts where we really didn't understand, and we did a bottom-up approach for that. And so in the end, you hope that you meet in the middle. But so on different levels, you can do like top-down things and bottom-up things. And I mean, I didn't really have that picture so clear in my mind back then, but I think it's good to understand what the benefits of both approaches are and what the downsides are. For example, like this homological algebra stuff was developed in a bottom-up approach. Like we knew we needed some homological algebra, and we just started developing it. And you can get quite far without hitting this issue by just always writing di plus 1 composed with di. And so that's what we did during the entire library development. But then you start using the library, and you just see, okay, every time I need to maneuver myself into a situation where I only use plus and never use minus. And that's just annoying. So there the bottom-up approach sort of failed because it was not informed enough about how things actually should be used. And so, yeah, we did a massive refactor of the library, which, yeah, I mean, it took a while, I guess a couple of days. And then we didn't just do one refactor, we really said that, okay, so now let's first think about how the library should actually behave. And we made several experiments, several changes, and then said that, okay, now this is what we want. We refactored the entire library, and since then, it has been a lot easier to use. Yeah.
So, I had a question about the refactoring. So you said that what is nice is that if you change the definition, you can check that you did not break anything. But so how much does it take for the computer to check that all the theorems are still correct after you?
In MATLAB, yes, for example.
If you have 1 million lines.
So Sebastian was talking about these pull requests.
Yes.
We merge on average about 20 pull requests per day.
Yes.
for every pull request that is made, there is some computer in the cloud checking that the new additions are compatible with all of Mathlib, and it compiles all of Mathlib. So this is checked multiple times per day, and I mean, this runs on pretty powerful hardware because it has to do all these pull requests all the time, and it takes a bit. Like on the Hoskinson Center, this hardware can compile
compiling method takes like 1.5 hours or something.
But on a huge computer. I mean, on
and if like you're changing something at the very beginning, so that it needs to recompile everything.
Yeah,
so
because if you add something on top, it can reuse the previous compilation and just check the stuff on top, and then it's done in 10 minutes or less. So on my computer, if I take a compiled version of Mathlib and I compile the Liquid project from scratch, that takes about half an hour. Yeah, but that's a lot. Like the Liquid project is quite large for projects.
So it means that even in the future, it will always be possible to check all the theorems in a couple of minutes or hours.
I mean, I guess like so hardware is still getting faster. I mean, Moore's law is stopping, but now we're finding other ways to still like be able to do more computations per second. So yeah, I
mean, I think we can look at this historically, and we have some kind of chart that shows how long Mathlib takes to compile. And like, it's been between 1 and 4 hours for the last few years. I mean, like sometimes Link gets faster, sometimes Mathlib gets larger.
Yeah, but probably yes.
If every mathematician on Earth starts checking every theorem they proved, and then we still have a scale issue. We will get. Yeah.
We're not there yet.
Yeah, we're very far from this.
I have a question. Like, is it possible to connect to other things like Sage or GAP or writing something in Lyon?
Right.
Did you use it?
So we haven't used that in the Liquid project. I know Rob Lewis together with Mi Chao.
Yeah.
I don't know the surname.
So.
Oh, okay. So he's written a connection with Mathematica, which means that you can talk about a function like sine of x squared plus 2x or something, and then you can get a plot of this function. And there's some other functionality that you can move back and forth between Mathematica and Lyon. And it's been on our wish list for a long time to connect with something like Sage or Paris or GAP or things like that. But it hasn't really, so far people just do this manually. Like if for some reason in some proof you need to factor a polynomial, then you just copy paste it, get the factorization, plug it back in Lyon. And in category theory, you have like this globular.io and things like that. And I think Scott Morrison has been using that to sketch out some proofs. And then he copy pasted an ASCII art version of the string diagram. But still, yeah, I think like at some point he sort of had ways to generate these link proofs so that you don't have to write everything by hand, but there's no software connection between globular and Lyon at the moment.
But also there are two levels what he was describing. For instance, if you want to factorize a polynomial, and it's nice if you can give it to Sage and Sage says this is a factorization, and then Lyon only has to expand to check that this is a legitimate factorization. But what would be even better would be to have everything done inside the proof assistant, but using an algorithm that has been proven correct and that is producing a proof at the same time as it's producing an answer. And that would be a lot more work, but this is also part of the science fiction future that we hope will happen someday.
Yeah. I mean, in the case of factoring polynomials, the proof is not so important, maybe. But for other things,
in that case, it's good enough to have a factorization and check that it works. But for some other problems, you don't have a DC certificate, so you need the algorithm to produce its own proof.
Yeah.
And in that case, it's more work. Because yeah, I mean, implementing a computer algebra system is also very non-trivial, and if you have to prove that things is correct, then it becomes complete science fiction.
Yeah, so you mentioned a certain point I don't know if it's dream of yours about extensibility for type theory. So is this something that you have thought about, that you have read about, that you have a clear idea of what your...
No, I don't have clear ideas. I mean, I've thought about it a little bit, but like I said, I've never really studied type theory, so I'm immediately on very shaky ground. So it would take me a bunch of time to get. I just notice the issues when I'm working with it, but at the moment I'm not in a position to work on solutions.
If there are no more questions, we'll have a break. I think we thank you, Johan, again first. Last.